Professor, you are so funny, ha ha ha.
Hello class, welcome back to Physics 101. We're up to episode number 5, and I'm pleased to present TJ Jin. Join us here in the studio. Good to see you, TJ. What brings you in today? I heard you were going to go into the lab. I wanted to stop by. Yes, we're going into the lab. We're going to see some very interesting things, some good stuff there. Lucy told me that you thought that I was better looking, and I agree with you. Just a joke, Doctor. Oh, you're not a doctor. You play doctor? You've been playing doctor again? Look at Professor, you're not a doctor. No, I'm not playing a doctor. I'm a Scientologist. A Scientologist. You know, a thinkologist? A physicist. I'm not a doctor. So say hi to Lucy for me. You know that Lucy, she's a real fan of yours. Yeah, she talks about you a lot. Yeah, she's amazing, isn't she? Nice to meet you, folks.
I'm so glad TJ came by the studio for this episode. The lab is where he did all the work for the treatise. You know, you could learn a lot from him, Professor. Tee hee hee ha ha, just kidding. I know you are smart too. Oy vey, I have to stoke their egos.
Yeah, Lucy, it was really good to see TJ. You know, and there's no two ways about it. He's a lot smarter than me. You know, a lot of ways I don't think I'd be here if it weren't for him. And some people say that it looks like I could be his brother, but I don't see the resemblance. Hello, class, y'all. Everybody come in, come in, come in. The taller ones in the back and the shorter ones in the front so everybody can see. Everybody can see. This is the Waveguide. It's an aluminum tube, and it's really tricky to get this thing configured right. You know, you got to have the grounding so that you have to understand that a waveguide is electrically conductive. But to keep the waves in place, okay, you got to ground the outside. Otherwise, you know, just transmit through the metal, and electrons really slow down when they get in a conductor compared to in a vacuum or in the open air. They go really fast. That's where they go the speed of light. Okay, so the idea is you got to get the waves bouncing down through the waveguide, and then they've set up what's called a standing wave. And the standing wave echoes back. Now when you get the waves synchronous, now you can measure the speed of light. Now you can see the difference between when they go non-synchronous and when they go synchronous. You're able to measure the speed. Now Lucy's going to give you a lot of details about how this all came to be and how it's all set up. And once again, Max Planck, the man with all the measurements, comes in. Him and Albert Einstein determined a lot to do with the speed of light. It's all about the length of the meter and time. Take it away, Lucy.
The waveguide is a cold-drawn aluminum tube. It is 3/4 of 1 inch in diameter with the wall thickness of 125 thousandths of an inch or 1/8 of an inch. There are PVC plastic insulators attached to each end, with rubber grommets attached to the insulators, into which transmit and receive electrodes are inserted. A 1 million ohm resistor and a 0.2 microfarad capacitor are at the receiver end, to tune the circuit to block the many radio waves that are in the air that cause noise. Since the lab is not in a grounded radio cage, some of the noise is unavoidable, but enough has been blocked to provide the readings necessary for these tests. What the professor is looking for is the verification that electromagnetic radiation propagates at the speed of light through air. A function generator is used to inject radio signals into the transmit electrode and then measured at the receiving electrode. The waveguide is a precision 1 meter in length. The current most accurate speed of light is 299,792,458 meters per second. How this was determined has been a source of debate for many years.
300,000 meters per second. It's 299, 299,792, 299,792. 300,000, Einstein, it's 300,000.
This stated figure of 299,792,458 is arguable, as the professor will show. First, how long is a meter? Are we sure? Second, are we sure how long a second is? These are interdependent and we must start somewhere. To restate, Max Carl Ernst Ludwig Planck, a German theoretical physicist whose discovery of energy quanta won him the Nobel Prize in Physics in 1918. He and Albert Einstein spent many hours arguing.
300,000 meters. 299,790. Einstein, 300,000.
Planck has been noted for so many quantizations they cannot be covered here.
And then the other issue is time. You know, how long is 1 second? 1001, 1002, you know? And then they came up with the idea that they needed an atomic clock, because they found out that cesium decays consistently, and the beat of the cesium decay became our time standard, and it's accurate to 9 places, 9 zeros. That's pretty accurate.
Let's just say the period of time we call the second is now measured by the decay of cesium. The TAI, or Time Atomic International, or International Atomic Time, maintains our time to 10 to the minus 9 seconds per day. Okay, now that we know what time it is, all we have to do is determine how long the meter is. You can read all about the history of the meter, but suffice it to say, in 1870 an international conference decided it all. A metal bar that is 90% platinum and 10% iridium, has 2 marks on it. When the bar is at the temperature of melting ice, the 2 marks are exactly 1 meter.
You know, that's pretty interesting how in 1870, the way they measured the meter was to say, we got a platinum iridium bar, okay, and we put 2 marks on it. And then we put it in melting ice to make sure that the controlled temperature is at 32 degrees or 0 degrees Celsius. And when those 2 marks are exactly at the right temperature, that's 1 meter. Warm it up, cool it down, it ain't 1 meter anymore.
In 1983 the definition of 1 meter became the distance that light travels in 3.33564 to the minus 9 seconds, or 1 divided by 299,792,458 meters. So, 3.3356 to the minus 9 seconds is 1 meter at light speed. The hyper-calculated number is shown. It has been a give and take proposition, and it does not really matter. Just pick a length, call it a meter, and let's all agree on it. The professor will show later how this is wrong, or rather inaccurate. The problem is time. It just won't sit still, and later we will see that the speed of light changes too. In the photo, a 15 MHz signal at 10 volts is applied to the transmit electrode. This is a very low voltage since we are only trying to transmit a distance of 1 meter, and not to Mars. There is an inline 50 ohm resistance coming from the function generator to load protect the generator against a short circuit. The impedance of the waveguide at this frequency is about 30 ohms. Here is the circuit. You can see the scope on channel 1 is set to 1 volt per division, and the 10 volt input signal is attenuated to 7 volts peak to peak. The received signal, full of extraneous radio noise, is running 70 millivolts. After traveling down the 1 meter waveguide, the received signal is the expected speed of light delay, or 3.3 nanoseconds. Thus confirming the theory that electromagnetic radiation travels near the speed of light, 3.3 nanoseconds or 3.3 to the minus 9 as shown.
So after several tries of getting the grounding right, measuring everything and adjusting everything, finally get to see on the oscilloscope there's a 3.3 nanosecond delay. That's the speed of light. Now let's look at deformation at different frequencies. Take it away, Lucy.
Another important thing of note is that a 15 MHz signal has a 19.98 meter wavelength. That is 20 meters for all practical purposes. That is found by taking the distance that light travels in 1 second, or 299,792,458 divided by 15 million, equals 19.98. The professor chose this frequency because of the even number length of waves. This is because the radio signal echoes in the waveguide to cause what is called a standing wave. For this test, the standing wave exactly matches the main wave. For a clear measurement, odd wavelengths produce standing waves that interfere with the source wave, that make it difficult to measure the 1 meter delay. The following slides show some different frequencies and the deformation of the observed wave. The standing wave combines with the source wave, which gives a summing of delays that shows approximately double, at 6.6 nanoseconds. It is important to note that electromagnetic waves combine to place the instantaneous amplitude at a sum of all wave forms. Now, instantaneous is perhaps a general term. You must define how long the instant is. That is, an instant is a window in time. If I look through a window that is only open for 1 nanosecond, I might see a voltage that misrepresents reality. And this is where the rubber meets the road, so to speak. Light does not combine its waveforms regardless of the time window and is not electromagnetic radiation. This will take more experiments to prove, but if it were electromagnetic, the professor states that he could build light circuitry. The only control we have over light is to turn it on or off and bend it through clear media. Yes, you can modulate a laser, but again it is on and off modulation, not frequency modulation. You cannot build a light transformer.
Isn't that fascinating how electrical waves mix together and you see the deformation? Electrical waves are real mechanical waves and they sum, where light waves never sum. Light waves are not electromagnetic.
Of note are the wavelengths. 16 MHz is 18.73 meters. 16.5 MHz is 18.16 meters. Up next is 17 MHz, which is 17.63 meters. Think of our precision 1 meter waveguide and take the ratios. 1 divided by 18.73 equals 0.053. The 16 MHz wavelength is 5.3% too large. As a result, the wave, which is 62.5 nanoseconds in time multiplied by 5.3%, is 62.5 times 0.053 equals 3.31 nanoseconds. The exact amount of the additional delay seen. If you make the waveguide 5.3% longer, the standing wave will fit perfectly, and the deformation will disappear. Now, one more image that is really interesting. When the function generator is raised to 20 MHz, the wavelength again is divisible by 1 meter evenly. Take the speed of light, 299,792,458 divided by 20 million, equals 14.98. This is close enough to 15, and look what happens. The deformation is only 1/2 of 1% or 0.005. This is 14.98 divided by 15 meters. Not only have we confirmed the speed of light, but the precision 1 meter waveguide, and the wavelength of 20 MHz being 14.98 meters.
And today we have crystal controlled clocks, which are pretty accurate, but they're not as accurate as the decay of cesium. So I guess we have to be accurate when you're measuring the speed of light. And later on we're going to see that the measurement of the speed of light and the time base, we find some problems there, okay? One is the introduction of phase velocity, which the physics And the physics professors want to teach that that's the reason that light separates through a prism, because of the phase velocity. But there's a problem here, because phase velocity doesn't exist. Okay, leave it to Einstein. I'm sorry, phase velocity doesn't exist. Okay, that's where the phase of the wave can go faster than the speed of light. In which case, then it would have to exceed the propagation velocity, and that never happens. So how does the phase go faster if the propagation is supposed to exceed it? No, it doesn't work. Okay, and I'm going to prove to you that the wavelet, the individual wave, doesn't know anything about any other wave. Okay, each wave is independent of the other wave. They got no brothers or sisters. Each wave is independent. So I call them a wavelet. A wavelet doesn't know anything about the wave that's coming behind it, and doesn't know anything about the wave that's in front of it. It's independent. Okay, and that wave still refracts. It doesn't have any relationship to any other wave, and it still refracts. And we're going to see why. And I like to say that the phase velocity exists in the twilight zone, not in Physics 101. Phase velocity does not exist.
The next point of order is that propagation velocity of energy has a frequency dependence. Stated again to be sure you are listening, propagation velocity of energy has a frequency dependence. If you are a knowledgeable physicist, you are angry right now, because every study has shown that there is no propagation velocity dependence on frequency, unless it is a diabatic heating of the medium. It is said that there is no frequency dependence, i.e., at 20 degrees Celsius or 68 degrees Fahrenheit, the speed of sound in air is about 343 meters per second, 1,235 kilometers per hour, 1,125 feet per second, 767 miles per hour, 667 knots, and this very complex topic has been researched extensively with so many variables. The frequency, speed dependency, is mostly theorized in ideal gas monatomic adiabatic models. Wow, that is a lot to explain. I'm going to try to simplify. Adiabatic is a process that contributes no heat to the medium the sound waves are moving through, because if you raise the temperature and expand or lighten the medium, the propagation velocity goes down, and if you cool the medium and it gets more dense, the propagation velocity goes up. So, if the sound waves heat the medium or ideal monatomic gas like nitrogen, lower frequencies cause more heat than higher frequencies, and you get a speed variation. So, why even consider sound waves? Because the propagation velocity is all over the map. In water, sound travels 4.3 times faster than in air, and in an iron rod it travels 15 times faster than air. Why not just stay with electromagnetic waves and light waves that travel consistently at the speed of light? These next experiments will take into account all wave motion and media, and will show that frequency has an extremely small effect on propagation, and even in a theoretical monatomic ideal gas experiment, the effect is so small that it would seem to not exist, but this oversight is the death knell to cosmology. It is a flaw that needs to be corrected. It is also the reason for the misobservation of the Big Bang and the universe at large.
And the second point, beyond discounting phase velocity, is that frequency is independent of propagation velocity. The propagation velocity and frequency doesn't make any difference. The propagation velocity is fundamental. And if you're a physicist right now, you're probably mad, because all of physics says the propagation velocity is fixed. In a medium, it's fixed. It doesn't have any frequency dependence. Now we're going to find out that that's not true. You know, when I was originally developing this thesis, and I came across the idea of doing the same thing in sound using a waveguide, I took the aluminum, which is a nice piece of aluminum aircraft tubing, and I glued the transducers with cyanoacrylate, this super glue, onto the ends of the tube, and I started doing the tests, and something didn't make sense because I was getting interference. I couldn't get a good standing wave. And what it turned out was I was broadcasting through the air in the tube and through the metal on the outside. So I'd get a double standing wave, which really took me a little while to figure it out, but that wasn't going to work. I'm going to have Lucy show you some nice pictures to show you, just so you can see the learning process of how I originally came up with the transducers on the aluminum tube. Take it away, Lucy.
Originally, the professor used the same precision 1-meter aluminum tube. Attached to the side is a temperature probe and meter. The piezo transducers are glued to the waveguide with super glue, which is cyanoacrylate. It gives a very good hard crystal bond to the aluminum. The piezo crystal is lead, zirconium titanate ceramic, and has the unique quality that when you apply a voltage the crystal swells. Apply a frequency and it oscillates. At low frequencies like 440 Hz, which is A above middle C, you can hear the pure tone. Because of its ability to oscillate at very high frequencies, it is the perfect device for these tests. The test will be conducted in the ultrasonic range, which is above human hearing. The reason for this is to get above all other noise that can interfere. The transducer also has the ability to produce a voltage when it is vibrated, which is why it is called a transducer, because it can transmit and receive.
Thank you, Lucy. So then, once I figured out why I was getting such a weird response on the oscope on the double waves going down through there, I came up with the idea of a different waveguide.
Discovery, you are along for the ride. As the professor analyzed the data, he had reason for concern that the device just presented had a problem. The concern was that the waveguide air chamber and the aluminum were giving erroneous data. He was seeing an interaction of frequencies transferring through the air for one velocity and through the aluminum for another. So, he regrouped and designed a new device out of a solid iron bar. It was worth it, and he wanted to share this process of discovery. He was astounded. When you are searching through the dark for a light switch, you know it is there, but it can be a daunting task. The new device. Early the professor discovered he needed to isolate the device. Any attempt to support it caused odd harmonics. The only way was to hang it from the very end. Attempting to hold it in the middle caused a double echo. He first placed the string supports on the bar about 1/4 distance, and it caused a quadruple echo. Supporting at the very end was the only solution.
So I went to a solid steel bar. Now this is a regular old piece of soft steel rebar. It's been cleaned up and polished on the ends so I could glue the transducers on. Now these are piezo transducers that you can buy online anywhere. And what they do is a piezo responds electrically. When you put an electrical pulse in it, the crystal snaps. Okay, so I use a square wave. I don't know if you see on the scope here. A square wave really makes the crystal snap, and I'm going to have the director switch over here to the microphone you see on the table, so you can hear what the transducer sounds like. Now I've got a perfect standing wave matching the input signal. That means the transducer fires the signal down here. This other transducer picks it up and fires it right back, and you get a standing wave moving back. Now this one is this transducer on this side is just as loud as the transducer on that side. It's just the steel transferring the vibrations. Mr. Director, switch to the microphone. 2536. That's the frequency that gave me a perfect standing wave. Now let's hear the other transducer. Just as loud. Transfers perfectly through the steel rebar. Now for the purposes of the video, we didn't do all the scientific controls we normally would. I didn't use the temperature monitor. We just turned it on. Whatever the room temperature was is the length the bar would be. You see, as the temperature changes, even when you're running a signal in it, the diabatic heating of the bar changes the length of it, and that changes the signal. It changes the distance that the sound wave has to travel. So in the controlled experiment, we maintained the temperature within a half a degree. Now, it doesn't make any difference which temperature you choose. You just have to, when you do your test, you pick your frequency, you determine the temperature, and that you have to maintain throughout the whole gamut of the tests, all the way from the low frequencies to the very high frequencies. Now, this pretty much brings us to the end of episode 5. In next episode, in episode 6, we're going to get into the details of what we found about the propagation velocity changing with frequency. Now, what's really interesting is that we found a fundamental here that works all the way up through sound waves, of mechanical waves, and I take mechanical waves all the way up to 20 million cycles. That's a mechanical wave at 20 million cycles that induces an electrical wave from the Earth's magnetic field. And then I'm getting too excited here. And then we take that all the way up into the electrical waves, and we start looking at the conductivity down through the bar and the way the waves, standing waves, move through the bar, and then we go right into light waves. So stay tuned. Episode 6 gets really cool. Thanks for joining me.